There's some questions though that are going to be nice and easy. Now, the one thing you got to be careful about, and in terms of your expectations, like we talked about last time, is the formatting. So we're going to have, a test on Blackboard, but here's a test that was a pencil paper test from, I'll say back in the day, but it wasn't really, it was only a year ago. So you guys got to understand it's going to be in somewhat of a different format, but it's not, what you see is pretty much what you get. All right. So I'll talk to you a little bit about the structure, and I'll talk to you about the words that I can't remember. Like I said, the resources. Focus. So anyway, numero uno, we have what is the formula to determine the mean of a binomial distribution, and are there any restrictions on the value of a probability? If so, explain what those restrictions are. All right. So on the breakdown, I said formulas for mean and standard deviation of a binomial distribution. All right. So something important to keep in mind is that I'm a man of my word. If I say that it's going to be mean and standard deviation of binomial distribution, that's the only way the question would be posed, then I'm going to stick to that. So all I would be asking for on your test is for you to state that the mean, and it could be in the form of multiple choice question, in which case, in the past it has been. So mu equals NP, and the standard deviation, sigma equals the square root of NPQ. All right, and so that's all the question would be asking. So that's kind of nice. Look forward to that sort of thing. But, in case you're wondering, they did, this version of the test did ask if there are any restrictions on the value of a probability. Well, that is a restriction, meaning is it limited to certain values? A probability, P of X, has to be between 0 and 1. All right, so this is impossible. And this one is certain. All right, so that would be the idea that somewhere between impossible and certain is where all the other probabilities would be. All right, so not what your question is going to ask, but it's something that you should probably know. I mean, definitely know. Otherwise, if you put an answer down, you do some calculations, you get a probability of 1.7 or something like that, and you're like, whoa, that can't be right. How would you know that can't be right? Probably because of something like this. All right. 4 conditions that must be satisfied in order for a distribution to be considered binomial. You have to have a fixed number of trials. You have to have a fixed probability. You got to have independent events. And 2 outcomes. For this kind of question on a Blackboard enabled test, I'm more inclined to put something in the realm of check all that apply, or which of the following is not a condition for a binomial probability distribution, that sort of thing. But these are the appropriate answers. If it's not one of these, then it's not something you should be indicating as an answer, no matter how intelligent it sounds. And I make my wrong answer sound pretty intelligent. So you just got to be careful about that. All right, but you have access to your notes, so there's no reason why you should get this one wrong. Really, numbers 1 and 2 are what I call indicator questions. All right, that has a meaning in my mind. The indicator aspect of that is that if you get them wrong, it's because you haven't like been doing anything. All right. It's an indication, or it's an indicator to me that you just haven't been like, yeah, I mean, you may have been on the Zoom, but you haven't been on the Zoom, you know. And that happens from time to time. You know, every now and then I'll get the old it happens mostly in the high school. It's kind of interesting. But you know, in college it happens too, where I'll be like, all right, it's time to end class. And then I'll have a staring contest with a couple of background images for a good 5 minutes of like, is there a question from the 3 people that are still here? And it turns out that they just muted the screen and they muted me and they just went on about their business and they kind of missed everything. It's really kind of those people that would end up paying the ultimate price. Not the ultimate price, of course, but you know, like the and ultimate price, not the ultimate price. So anyway, these 2 indicator questions, I go into every assessment thinking everybody better get these ones right. All right. So you don't want to be the one that gets this wrong. All right. Number 3, if the following is a probability distribution, compute the mean and the standard deviation. If it is not a probability distribution, explain why. So what we're going to do is we're going to go on over to our Desmos calculator. And we have a few different options from the announcement that I posted on Blackboard earlier. Well, I posted it over the last couple of days, but I posted the most recent one earlier, like as in 20 minutes ago, half an hour ago. But I'm always tinkering with Desmos just to see if I can come up with a better option. And so what I recommend you do is you go into Blackboard, you click on those links. And when you click on those links, you have the option to save those links. You save them as your own file, right? And so I've already done that because they're my files to begin with, but you can save them so that you have them ready to rock and roll for the test. All right. So number 3 is talking about a probability distribution. All right. So what I can do is I can stop this share and go on over to my Blackboard share. Eventually. Show you what I'm talking about here. And tells you. You can save my file and use it as a model, and you can use it to do the work also, you know. So, and I kind of designed them so that all you'd really have to do is replace the numbers in my examples with your numbers, and then you're good to go. All right, so supposed to be helpful. That's the plan. You know, best laid plans though. All right, so we have right at the top here is updated in all caps, so you know I mean business. All right, so we have probability distribution for mean and standard deviation on Desmos. So that's what would come up. You see, you got this whole setup here, but it gives you a population mean and a standard deviation. So that's all well and good. All right, but what you would do if you want to save this, because I'm already logged in. If you haven't logged in, you know, created an account and logged in, then we are definitely squarely in the territory of, okay, what are we waiting for here? You know, create an account and make sure you're logged into your Desmos. Otherwise, you're not saving your work. All right, and then once you do that, you can click on the little menu bars here. And, you know, it's my file, so I don't need to save it, but it'll be highlighted in green here as an option to save. And then it'll save it. And then it's yours. You can retitle it if you want. You know, I got a ton of files that look very similar to one another. So it's kind of dangerous when that happens. You know, it's like, oh, okay, which one of these probability distributions for the mean and standard deviation is the one that I'm interested in? So, you know, one day I'll sit down and clean this all up. Like, for example, I don't need the untitled graph that's here. I'll give you a second just in case, you know, you change your mind. couple untitled graphs, clean it up a little bit, but it should be there, and that's the plan. All right, and so do that again. So I'll just I'll just go back into Blackboard from another window. Of course, I got to click on like 17 different things to get there, but that's the way the mop flops. I don't know if people get that reference anymore. Binomial probability Desmos. So you click on that one and you save it. So again, save me. And then you do it again. I'm just doing it the long, boring way. Because I set it up to not open a new tab, which I regret now. But what can you do? I mean, I could change it. That's what I can do, but I'm not going to do that now, is what I'm saying. All right, so I got my 3 different things. These are the recommended ones that you're definitely going to want. So you save them, and boom, they're all there. All right. So then what I'll do is I'll go into my other Desmos, and you'll see, it's all saved in the cloud, as they say, the mysterious cloud. Here, play. All right, so I got this stuff here. I got all this data here. So I gotta look in on that. All right, this data has to make its way into my calculator. So what I would do is, for whatever reason, feel like I'm trying to tap on the wrong thing, and go to my most recent 3 files are the ones that I just stored in there. Now for you, unless you're a Desmos guru, you're probably only going to have a handful of saved graphs. The most recent 3 of them should be the 3 that you just moved over. All right, so you tap on the probability distribution one. All right, now one thing that you're going to want to take into account, well, a couple of things you're going to want to take into account. One is that sometimes it could be kind of a pain to overwrite values using a tablet, which is what I'm using right now. So just be careful and be patient. If you do have a separate device like a laptop, it tends to work a lot easier. But that's up to you. If you can navigate through with an iPad or something like that, that should be fine. And this one starts at 1, so. So yeah, just a little patience goes a long way here. So I just need that second 5 to go away, and I'll be a happy camper. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I need everything beyond the 9 to go away. So that I can just backspace on. All right, so I got I believe the first 2 values in. I didn't really need the 0 in front, but whatever. This one. 0.1249, then 0.0969, 0.0792, that's the 5th one, okay. .058, 0.0512, and then 0.0458. All right, I got that stray value there. I want to get rid of that. And then I definitely want to have another look. I'm going to kill that 0 in front there. So 301, 1761, 1249, 0969, 0792, 0669, 058, 0512, 0458. All right. Now, as I was editing that, it was spitting out the mean and standard deviation for me. Right. So that's great. The problem is I don't know going in whether or not it's a probability distribution to begin with. So that's kind of where I want to start. All right. So a probability distribution needs to have the sum of the P of X values equal to 1. So if the sum of the P of X values is equal to 1, then it's a probability distribution. So I need to verify that because I already have the mean and standard deviation. So like the hardest part of this problem was typing in data. Once I had that taken care of, then it was going to be fine. But the problem is, I don't know if it was necessary to make that determination, in terms of the mean and standard deviation. So I gotta test this out. So I want to say, is it true or is it false? All right. So one way to do it would be to just grab a calculator and just start adding those values up. But you see in my computations here that I have a total, the total represented a few times. Total seems to be exactly what we need. All right. So I could just create a new cell here and just type in total. The only thing Desmos ever wants is for you to tell it what you want it to do with the command. So total what? I want it to total the Y1 values. All right, so I got all these Y1 values. So I'm going to total them all up. Y1. It does equal 1. All right, so it is true. All right. So that's my license to say mean, standard deviation, and then I just grab them from Desmos. 3.441. If we're rounding to 3 significant digits, just be careful about rounding instructions. All right, 3 significant digits would be 441, and then 2.461. All right, but this stuff here doesn't happen unless the sum of P of X is equal to 1. All right. If you got anything other than 1, you wouldn't report the mean and standard deviation. All right. So in that regard, it can be kind of tricky because you might get a mean and standard deviation, be like, oh, that was an easy one. Completely wrong because the P of X column didn't add to equal 1. So be very careful about that. So 3 down. Yeah. First 2 were gimme questions. The second one, like there's a little trap there, but if you're careful, then you don't fall into the trap and you're good to go. All right. Then we get to the juicier ones. A coin is flipped 5 times. What's the probability that at least 3 of those flips turned up a head? Turned up a heads. All right. So, we're diagnosing. We're always diagnosing. It's a question of, all right, well, what kind of problem is this one now? It's always going to come down to that. It's like, all right, if we could figure out what kind of problem it is, at least you got a fighting chance. All right. And unfortunately, I only told you here, probability question involving at least at most. So in terms of the breakdown. So it's a question, okay, well, thanks for that, dude. Probability at least. Okay, yeah, well, he wasn't lying, but how do we do it? So we're going to take a look at this. And first off, I'm going to go back over here. I'm going to grab these 2. Or not these 2, these 4 actually. And I'm going to see very quickly if these rules apply, because if they do, then I know what kind of problem I'm dealing with. If not, then I'd be kind of at a loss. So I'm kind of rooting for binomial. All right, so fixed number of trials. Well, a coin is flipped 5 times. Sounds good to me. It means n is equal to 5. We've satisfied that little bit of criteria. The probability that at least 3 of those flips turned up a heads. Fixed probability. Doesn't seem like it might be at first, but it is, because the probability of getting heads when you flip a coin is going to be 1/2, unless they said that it was some kind of trick coin or something like that. But that's not what was said here. So it's fixed probability. The probability is going to be of getting a heads equal, probability of getting a heads is going to be equal to 1/2. So we're good there. This is getting worse and worse. I'm just going to leave that. Independent events. Well, if I flip a coin 1 time and get a heads, it doesn't mean I can't flip it again and get a heads and again and again and again. So it's not like cards where after 4 cards it's possible I could be out of kings, you know, there's only 4 kings in the deck, you know, so this is not that. So we're looking at independent events and 2 outcomes. Well, yeah, coins are like the definition of binomial. It's heads or tails. All right, so we know that it's binomial now, but the trick to it is suspecting that it would be binomial initially. Because if you go into a problem not having the suspicion that it could be binomial, then that could be a problem. But you just want to have it on your radar. You want to be thinking, okay, well, maybe this is a binomial case. So we'll take a look. All right. But once you've identified it as binomial by whether or not it satisfied these 4 conditions, then it's really just a matter of going to your Desmos calculator and getting to work. For this one, you know, it's really up to you. You don't have to go too crazy with the ones that I wrote, because it's a simple, you know, computation on Desmos. But I'll take you through the ones that I made also. So we want to know the probability of at least 3 of those flips turning up a head. So probability of at least 3 heads. All right. So I'm going to just put that in simple terms here. That's the same as saying probability that X is greater than or equal to 3. All right. Now we're only rolling the die, or I'm sorry, flipping the coin 5 times. So if X is going to be greater than or equal to 3, that only gives us a few different options. That would mean that the probability would be of X being equal to 3, or X being equal to 4, or X being equal to 5. All right, because again, it's 3 or more, greater than or equal to 3, at least 3. But there is a maximum because you're only flipping the coin 5 times. So it's a maximum of 5 flips. So if you were to, you know, flip a coin 5 times, if I were to ask people, I would say, okay, if I'm going to ask you to flip a coin 5 times, tell me how many heads you got. And then you come back with, well, I got 7 heads. Like, I think you might have made a mistake or misunderstood what I was asking, because I only asked you to flip the coin 5 times. How on earth did you get 7 heads? Right? The best you can get is 5 heads. Right? That's what's going on here. Right? So we could figure out each of these probabilities, or we could use the binomial probability calculator. All right. Now, I tried to make sort of catch-all Desmos scripts without it being too confusing. But I also didn't want to get too many things into one script, because I knew that would drive people nuts. So if you look at the binomial probability, see, you have number of trials, probability of success, minimum number of successes, maximum number of successes. I created sliders for that to make life easier. If you have exact amounts, then you would just make the mins and maxes the same number. All right, that's what we did last time. All right, here we got 5 trials. All right, well, my default was 5 anyway, so that's fine. The probability of success is 0.5. So slide it to 0.5. If it ends up sticking and hopping on you like it's doing for me, then just give up, quit, call it a submit. No, just type it in. Tap on it and type it in, and then I hit enter. I just out of habit, and then it creates a new field. So I just X that out when that happens. Minimum number of successes, well, that would be 3, right? Because I can't go any lower if I'm going to have at least three successes. So this would be my minimum, and this would be my maximum. And collectively, we're going to get all of this information. So I'm going to pop in 5 here. Collectively, we're going to get all of this information popped into our binomial probability formula. All right, so if you kind of look at it, you say, all right, we got my number of trials, 5. Probability of success, 0.5. So that goes back to what I was saying here. All right, so N, probability of success. Doesn't ask for probability of failure because it's automatically going to compute that. Minimum number of successes 3, maximum number of successes 5. Check, check, check. So whatever it says in binomial dist, so binomial distribution, whatever it says as a result there is going to be your probability, or going to be your probability. So we could say here that the probability that X is going to be, well, I could just say at least 3 heads. I want to actually put it in the answer the question that's being asked. That makes more sense. So the probability. Yeah.
Why the probability have to be half, like 0.5?
Because when you flip a coin, your probability of getting heads is 1/2, which is 0.5 in decimal form.
Got it. Thank you.
No problem. So as it turns out, the probability of getting at least 3 heads when you flip a coin 5 times actually ends up being 0.5 anyway. It's kind of surprising, but it is a possible outcome. So that can happen. And this would be, you wouldn't necessarily want to do it, but this way, but the alternative would be, it's not really pretty, and I'm not going to do it all, but I'll get you started on it, and I'll show you just how much you don't want to do it this way. You'd say, okay, I'm flipping a coin 5 times. Well, I guess they could all be heads. 2, 3, 4, 5. Maybe the first one's heads, and then it's all tails after that. Okay. Maybe a couple of heads, a tails, and then a couple of heads. Maybe it's that. Maybe it's that. I will tell you that there are 32 possible sets of 5. So I'm only 5 in. So, and 27 more. All right, so it's either you do it with the binomial rule, and considering that the calculator that I gave you, the Desmos calculator, is pretty much going to do it for you, why not, right? Why not make use of that, right? Because the alternative is to, write it all out like that, which would be terrible. Right? You could also make a tree diagram too. Not much better. That's not somewhere you want to be living when it comes to this concept. All right. Number 5. So another binomial case. So it's like a lot of binomial stuff, but it was kind of the culmination. I mean, it was definitely the culmination of the unit. Now, I'm just making sure. Okay, yeah, because sometimes I change up the sequence of questions from semester to semester. I just wanted to make sure that this test was in alignment with the breakdown that I gave you. All right, so psychology quiz contains 30 multiple choice questions with 4 choices each. You decided not to study because you're too busy preparing for a statistics test. So you need to guess the answer to every question. Or if you're like me, you just didn't study because you didn't want to. Determine the number of questions that you would expect to get correct. All right, so expected value. That's the same as the mean. All right, so once you identify this as another binomial case, and that is part of the challenge, you identify it as a binomial case, then you have license to use every shortcut that goes along with a binomial situation. All right, so something to keep in mind. Again, I tend not to be a liar when it comes to my breakdowns. Usual, unusual, involving binomial probability. All right, so you don't need to verify the fixed number of trials, fixed probability, independent events, and 2 outcomes because I'm already telling you going in that it's binomial. However, it's a good thing to keep in mind. All right, so fixed number of trials. You're taking 30 a 30 question quiz, so n is equal to 30. Fixed probability, 4 choices. Probability of getting it correct, because probability P is probability of success. You have a 1 in 4 chance of getting it correct, which is 0.25. Independent events. Now we got to make an assumption here, and that is that getting 1 question correct or incorrect is not going to have an impact on whether or not you get other questions correct. But, you know, common sense tells us that, you know, if you get a question right, it may be because you knew that material. And if another question is related to that concept, then you stand a better chance of getting that right. However, this is under the assumption that you're guessing on every single question, right? So we can say independent events. And we could also say 2 outcomes. 2 outcomes is the easiest thing to really kind of identify. It's right or wrong. All right. Even if there are multiple ways to get a right answer, it's still wrong or right in some capacity. You know, you could always kind of manufacture a binomial situation, right? But once you identify that, we now know that it's mu equals NP is our formula. It's really just a question of, okay, how do you want to do it? Because I got a calculator here that's going to give me the mean and the standard deviation, which I'm going to need in the next part. So you may want to do it that way, all right? Or you could just compute it by hand. It's not challenging, you know. I mean, you're going to probably compute it using a Desmos calculator anyway. But if you wanted to, you know, calculator on your phone or something like that, you're going to get it either way. So 30 times 1/4 or 0.25. I'll use the 0.25. It's going to be 7.5. All right. But I'll use the dials on this one here. So 30 questions. Probability of success is 0.25. And if you scroll on down, you see that the mean mu equals NP is 7.5. Oh, and by the way, these scripts that I'm giving you on Desmos, you know, if you haven't picked it up already yet, I mean, the mean and standard deviations, which are going to be question 1 on the test, are in these calculators. So I'm basically giving you the answer. I mean, aside from just the fact that you can reference them in your notes, I'm also giving them to you in the Desmos calculator. So there's really no excuse for getting those questions wrong. All right. The shame that I will be feeling, you know, it would be kind of like like ashamed, like I won't be feeling shame. I'll feel proud that I did everything I could, but I will be ashamed. So I will feel the shame for you, right? Is what I'm saying here. That's kind of how that'll play out, right? I will feel terrible that that you took my gift, you crumbled it up, and you threw it in the garbage right in front of me, because that's pretty much what you would have been doing, right? So determine the standard deviation of the number of correct questions. Sigma is equal to the square root of NPQ, or as we've come to know it also, NP times 1 minus P. They mean the same thing, because Q is the probability of failure. 1 minus the probability of success is the probability of failure. All right. Either way. All right. So if you want to pop it in, you can do that. You could say sigma is equal to the square root of 30 times 0.25 times 0.75. Your chances of getting it right are 1/4. Your chances of getting it wrong would be 3/4. Right? 3 out of 4 are wrong, right? So there you go. You can get the answer from your personal calculator, or you can get it from right here. I'm staring right at it. 2.372 approximately. All right. So then we want to get the usual, unusual stuff. So would 20 correct questions be considered unusual? So let's pop that in. We need to compute mu plus or minus 2 sigma. So got my mu, 7.5, plus or minus 2 times my sigma, right? Yeah. And you can crunch those numbers any way you want. What a lot of people will do is make use of what they have on their Desmos calculator. All right. So 7.5 minus 2 times 2.372. And then do a little duplication. Change minus to a plus. And you got those two values. All right, so and this stuff, just so you know, this stuff on the Desmos calculator, it doesn't get saved unless you save it yourself. All right, so that's kind of, it's a good news, bad news kind of thing, because if you really want it to be saved, it's not going to get saved unless you actually make the choice to save it. All right, so just be careful about that. All right, so we're looking at, oh, that is not a pen. On the low end, 2.756. And on the high end, 12.244. Oh, close bracket. This is the usual interval. All right, so the usual values fall between these two numbers. So I would say, therefore, 3 dots in the form of a triangle means therefore 20 is unusual. All right, and I've supported my answer already. All right, so would 20 correct questions be considered unusual? Yeah, it would be unusual. So if you were to guess on a 30 question multiple choice assessment, you can expect to get somewhere between roughly 3 and roughly 12 of the questions right. All right, so somewhere between a 10% and like a 35 to 40% of those questions right. All right. The 20, I chose that because that's in the passing range. So it's unusual. So anything above that number, 21, 22, 23, all the way up to 30 would also be considered unusual. And so therefore very unusual to expect that you would pass if you were to guess on a 30 question multiple choice assessment, right? Even with 4 choices. All right. And you'll see, even if it was a question, I'm sorry, a true false assessment, like 100 questions, your chances of getting a passing grade just by guessing very, very remote. All right. So number 6 is that simulation question. So we got to get rid of that one and replace it with something more meaningful. So let me keep going for the mouse here. It's not going to work. I'm not using that device. Understood. Not a problem. So the next one up is an addition rule question. So let me create an addition rule question right now. All right. I'm gonna pop a few diagrams in here. If I can make a few diagrams. I didn't turn my tool on here. That one didn't work. There we go, close enough. And then let's do a couple of these. Yeah, good enough. Didn't have to be too crazy. I just wanted to have a couple of different varieties. All right. So the addition rule question would be, for example, find the probability. Oh, that's not a P. Find probability of getting a red figure or a triangle. All right, and it's only one item selected at random. All right, so one selection. That's the hallmark of an addition rule situation. It's a single item, and then you have multiple possibilities. All right, so the first thing that you would want to do is identify whether or not you're dealing with a case that's mutually exclusive, or at least consider that. You don't have to write that for me. You just want to be thinking about that. Basically, is there any overlap? Right? Is there a way that you could have a figure that is red and also a triangle at the same time? And the answer is yeah, we got a couple of them. All right. So what I would do, if I'm applying the addition rule, and if a question is asking you for the addition rule, the expectation is that you would show addition in that addition rule. All right. So we're looking at, let me just bring this up a little bit here. The probability of red plus the probability of a triangle but then I'd be looking to subtract off. This is, one of the ways that we did it, when we learned how to do it. The probability of being red and a triangle. All right. So there's a total of 6 objects. Let me get rid of this. There's a total of 6 objects. 1, 2, 3, 4, 5 of them are red. 1, 2, 3, 4, 5, 6, 7, 8 objects. I don't know where I got 6 from. All right. Then I look at the triangles and I say, okay, how many triangles do I have? I got 3 triangles out of the 8 objects. Bearing in mind that we do have some overlap. We have a couple of instances where the triangles are red as well, right? So they're triangles and they're red, all right? So I would want to subtract off those. So I'd be looking at 6 out of 8 as a result. Just double checking. Yeah. All right. So that's using the addition rule to actually figure out the probabilities. You just got to be careful because depending on the directions, you know, if it's multiple choice, then it could just be find the probability, in which case you're like, okay, well, how many do I got? And I could be like, all right, well, I got, I'm looking for a triangle and I'm looking for something that's red. Well, 1 red, 2 red, 3 red, 4 red, 5 red. Now let me make sure I got all the triangles. Well, there's my 6th item that I need. Basically, I need everything except for the circles and I'm sorry, the blue circle and the blue ellipse. You could do it that way, but if the question says using the addition rule, you got to show the work, right? So, you know, it's a question of directions. It almost always boils down to that. You know, you think about any kind of math test, it's like, well, if I could do it this way, it'll be fine. But if I got to do it that way, it's going to be a nightmare, you know? I wouldn't call this a nightmare, though. It should be all right. All right. So then next up is the conditional probability question. This is another one of those, we call it an indicator questions, because the idea is that, dang, you better get this right. Right? Or at least you better get something that's representative, something that's close to right. Right? Because all you have to do is give me a probability. There's really no work. It says, given the following contingency table, determine the probability of heroin given the 18 to 25 category. Data comes from substance dependence for, so it's real data, right? So, it's kind of morbid that I'm using this as a question on an assessment because it's kind of serious business, but it is what it is. All right. So we're looking at the given is the 18 to 25. So that's this column. This is the given. All right. So only from the set of 18 to 25 are we looking for the probability of heroin, whatever that means. You know, in this case, it's a substance abuse specifically related to heroin. So what I would do is just basically pretending like no other aspect of this table exists. So I disregard this, disregard this, disregard this. I'm looking for how many of the individuals in this set are heroin users. In this case, we're looking at 47 folks. And how many are in total for that category? 25, 26. All right, so it's really just whatever the second thing is, the second item in your probability question is, that's going to dictate what part of the table you're working with. And then from there, you just address the first part of the probability statement, in this case, heroin. All right. Now, number 8, you see a whole lot of space here for number 8. That's because it's asking you to do a tree diagram or list of sample space. Most people prefer the tree diagram. I will say that on Blackboard, when it comes to answering a question like this, it almost always is easier to do the sample space because you're just listing out values. All right. So we're rolling a die, all right, for a roll of a die followed by 2 tosses of a coin. All right. So if we were to do a tree diagram, it would be a roll of a die. So the numbers 1, 2, 3, 4, 5, 6. Then I'm flipping the coin or tossing the coin twice. So I'll just say toss coin 1. And then, toss the coin a second time. All right. So if I'm tossing the coin the first time, my outcomes are heads or tails. All right. So then from there, I can toss a coin a second time, in which case I still have outcomes heads or tails. Even using my technology here still takes a second. You get there though. So that's fine, but like I said on Blackboard, and by the way, I'm not going to ask you to do something this lengthy because I know on Blackboard it's a pain. When we did it with pencil paper, it was like, all right, well, we got time, we got space, so let's just do it. But if we were to do it as a sample space, sometimes folks like to create the tree diagram first to organize their thinking, but it really would be just listing out every one of these possible outcomes. So 1HH, so you're just following every pathway. So 1H followed by an H, then 1H followed by a T, and then working your way down the line. So 1HH, 1HT, 1TH, 1TT, and then doing all that same stuff again, just with 2s, 3s, 4s, 5s, and 6s. All right. But once you get the idea that it's HH, HT, TH, and TT, it's like, all right, let's just do that for the 2s, 3s. Kind of going askew on me here. So 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4. Five, 5, 5, 5, 6, 6, 6, 6. All right, so you don't have to do both. It's one or the other. Oh, what did I just do? Wrong class. You just hopped on me. All right, there we go. In case you're wondering, I have students with names in other classes. So anyway, yeah, that's what the sample space would look like. It's not fun, but it's doable. And just typing a list of values like that is much more manageable, I'll say. So this is an or. You don't have to do both. All right. That's it. A couple more. Number 9 is multiplication rule. Multiplication rule is the number of outcomes in a sample space for number 10. Kind of finish strong here. They're not too bad. 3 geometric figures are selected from the sample space below without replacement. What is the probability that none of them are triangles or hearts? All right, so multiple events means multiplication. No, multiple events means multiplication. All right, so what is the probability that none of them are triangles or hearts? So we got to think about what that means. None are triangles or hearts, which means that it is not the case that they're triangles and hearts. All right. So what I want to do is I want to ignore triangles or hearts. All right. So we do not triangles and we do not want hearts. I can't make hearts. It's not in my wheelhouse. I could have copy and paste it, but I'll just copy this one. This is slightly better. So what I would do is I would eliminate triangles and hearts from the set. All right, so I don't want triangle. That's not a pen. I don't want the triangle. I don't want the hearts. Here's another triangle, kind of sneaking in there on me. All right, everything else is fine. So I have 3 possible items that I could be dealing with. So the first one, probability that, again, none are triangles or hearts. It's going to be, and again, there's 3 figures. So I have a total of 12 objects. It's without replacement. So we think about what I have and what I want. All right. I have 12 items. I only want 9 of them. After I select one of the items that I want, let's say it was that big old circle on the right-hand side, that big old circle on the right-hand side is no longer available. All right. So I would be down to 8 objects that fit what I want, but I would also be down to 11 objects in total. I'd also be down, once I select one more, so let's say it was that pentagon in the lower right-hand corner, I'd be down an additional value, so 7 out of 10 remaining objects. All right. And you could play it out like that. You could say, okay, well, let's say I get rid of this one. What do I have left? I would have 1, 2, 3, 4, 5, 6, 7, 8. All right, that's where the 8 comes from. All right. And then you would say, okay, well, what if I got rid of this one? So then I would say, okay, what do I have left? 1, 2, 3, 4, 5, 6, 7. So that's where the 7 comes from. Then it's just a matter of multiplying. All right, do it any way you want, Desmos or by hand. If you do it on Desmos, and my recommendation would be to do it all in one shot, create the fraction tool, 987. You could also do the, use a permutation, but there's only 3 values, top and bottom. It's not too difficult to type it in by hand. And then again, if you get that little fraction icon, that means that there is an available fraction equivalent to the value that you just came up with in decimal form. So the fraction answer is always going to be preferred. but you can toggle back and forth. All right. But if you round this to 0.382, for example, that's slightly wrong. 21/55 is more correct. All right. So you just got to be careful, especially if it's multiple choice, because you don't want to run the risk of getting something wrong just because, you know, like you rounded, you know, that would be pretty bad. All right. And the last one, how many events are in the sample space of 3 rolls of a die followed by 4 flips of a coin? This is also kind of a gimme. All right. What I'm looking for here is you to apply this rule. And we talked about this early on in the unit. Number of outcomes per trial raised to the number of trials. All right. The only thing is we got 2 things going on here. We got 2 events going on here. All right. 3 rolls of a die, then 4 flips of a coin. All right. So we'll talk about the 3 rolls of a die first. 3 rolls of a die. One roll of a die has 6 outcomes. All right. And we're rolling that die 3 times. All right. Followed by 4 flips of a coin.
Yes, sir.
Hold on one sec, folks. Yeah, what's up, bud?
Okay, I submitted my exam.
Okay,
In
cool.
the first attempt, I wasn't able to. I was trying to do like put the pictures all inside of the Word document, so I wasn't able to submit the pictures. So everything went on the second attempt.
Okay, that's fine.
All right. Thank you. Have a good night.
You too, bud. All right, well, at that point, it's a good idea to check the chat because I see, how do we know to use multiplication for this question? What was our keyword? No, the keyword was the fact, it wasn't really so much, and so going back to number 9, it wasn't so much, with replacement, without replacement, I guess, could have been a key phrase, but it had to do with the fact that there were 3 objects being selected. All right, so that's multiple events. So multiple events leads to multiplication. All right. So the fact that it's without replacement only happens because you're having multiple events. So that's kind of a byproduct of the fact that there's multiple events. But I suppose you could use that. Either way, it's
Can we determine by the flip of a coin too, for it to be a multiplication rule?
In most cases, when you involve coins, it's multiplication rule, but it doesn't always play out that way. But it's pretty good thought.
Okay.
So we have 3 rolls of a die, and we have 4 flips of a coin. Yeah. So the followed by, again, means multiple events. So we're going to multiply again here. 1 coin has 2 outcomes, but we're raising this to the 4th power because we're flipping it 4 times. All right, so this can get popped right in. I'm just making sure I hit record again. So 6 to the 3rd times 2 to the 4th. And then you get a result of 3,456. In terms of computation, this really isn't that difficult because you're just carrying it out using calculator. The idea behind having this question on an assessment is just really kind of force you to consider just how many items would be in a sample space, because even just going back to that one, the binomial probability case, like once you find out that there's 32 possible outcomes, most people look at that and say, well, I'm not listing out 32 possible outcomes. It's terrible. Now imagine there's 3,456 possible outcomes and there's a probability question related to that. You're definitely not going to want to list it out. All right. And that's only, I mean, this is only dealing with dice and coins. You know, it could be way more complicated. So we just want to be careful. But The question on the test will be specifically along these lines. Maybe it's not going to be 3 dice and 4 flips of a coin. Could be 2 rolls of a die and 4 flips of a coin.
Okay, yes, I was just about to say, can you just leave them like that and just change the numbers?
I might change the order. You know, I might make it, you know, the coin coming first, then the dice.
Okay,
You know, I might do like 2 rolls of a die followed by 2 flips of a coin followed by 3 more rolls of a die. You know, something like that. But it's all going to have the same kind of look and
I
feel.
need to get a good grade on this because I sucked the first test, please.
Yeah, there you go. But we'll get you there.
Okay.
So that's really the test. I mean, if you study this and then work on the other review problem sets, which are basically more of the same, then that should set you up pretty nicely for the test. Right?
This test is in the shared drive, right?